Hello. So it's a new week and we will resume with our new chapter, chapter 5, which is all about work and energy. So let's review a few concepts. So work, we agreed that work is an energy transferred by a force. By definition, how do we calculate work? If there is a force that is moving an object a distance delta x, then the work is the x component of the force vector times this delta x. Okay. In this special example, F is along delta x. So W in this specific example, W is all of F times delta x, because as you see here, F is along delta x. Okay, if we take another example, let's calculate the work done by the normal force. Okay, let's calculate the work done by the normal force. Work done by the normal force is equal to nx times delta x, but we all know that nx is 0 because n is along the y-axis, so this is equal to 0. Same thing for work done by weight. I'll write it as weight just to distinguish W from W. Okay, same thing, this will be 0 in this case, in this particular case, because it is perpendicular to the line where the object is moving. Okay, so this is our delta x, our x-axis. We always take it along the line of motion. The box is moving this way, so x is this way. Okay, we also agreed that work can be negative. Work can be negative if the force applied is resistive force. It is resisting the motion. And one example of resistive force is what we know by now, friction. So if there is a friction, then look at it, Fx, that is the friction of this, the x component of friction is minus F, because it's along the x-axis, but in the negative direction. So the work done by friction is Fx delta x, which is minus F delta x. So work can be negative as well. Okay. If the force is making an angle theta, then Fx will be F cosine theta. Let's solve an exercise from the booklet. So a man pulls a sled loaded with salmon. The total mass of the sled and the salmon is 50 kilograms. So we have mass equal 50 kilograms given. And the man exerts a force of magnitude 120 Newton on the sled by pulling on the rope. So if you see the drawing here tells the story. Part A. How much work does he do? So we want to get the work done on the sled if the rope is horizontal to the ground, theta equal to 0, and he pulls the sled 5 meters. So here they're saying that theta is 0, okay, and delta x is 5 meters. What does it mean theta is 0? It means if this is my object, okay, if this is my object, let's put it in another color. So if this is my object, okay, theta is 0 implies the force is in this direction. So this is F. Okay, so to calculate the work, and this is F, and it's moving along this axis. So we can draw x-axis, it's in this direction. So Fx in this case, so W is equal to Fx delta x. W is equal to Fx in this case is all of F because it's all on the x-axis times delta x given to be 5. I replace F by 120 Newton. and I get my work equal 5,600 joules. So the unit of work is joules. Okay, this is part A. Part B, let's do it up here because we need space. How much work does he do on the sled if theta equals 30 degrees and he pulls the sled the same distance? So theta this time is a 30 degrees. The force is the same. The force is the same, 120 Newton. And the distance is the same, delta x equal 5 meters. Okay, so we also draw. So now this is my object. The angle is 30 degrees for the horizontal. This is my force F. Okay, so the object is moving along the horizontal line and the force is making an angle theta. So we have to draw our x-axis. Okay, this angle here is 30. Degrees. So how do we get fx? As usual, we move on the x-axis until we reach the tip. So we move along the x-axis until we reach the tip of the vector. This is fx. And it is adjacent to angle 30. So fx is f cosine angle 30, where f is 120. So I get fx is equal to 104 Newton. Now I come here and I do the work. Work is fx times delta x. Work is equal 104 times delta x, which is 5. I get work is equal 520 Newton. Notice that now the work done by the force is less, right? Because when it was along it, it was causing more. It was causing we can see that the work will be higher. Okay, as we start changing theta, as we start increasing theta, the work will start decreasing until I reach theta equal 90, and in that case the work will be 0. For example, for the normal, the work will be 0. Okay, part C, let's do it here. At a coordinate position of 12.4, so at x initial equal 12.4 meter, the man lets up on the applied force. So no more force. Okay, no more force. A friction force of 45 Newton, between ice and the sled brings the sled to rest at a coordinate position of 18.2 meter. X final equal 18.2 meter. How much work does friction do on the sled? So we want W by friction. We agreed that it will always be minus F, because if I draw it, let me draw it first to show you. So if this is my object, now friction, you only have to draw the force in order to get the work by it, okay? So if I draw the force of friction, and the object is moving from x initial 12.4 to 18.2, so it's moving in the opposite direction. This is friction. Let's stick to the same colors so as you don't get confused. And this is the x-axis. Okay, now the work done by this friction is Fx times delta x. Fx is minus F because it's opposite to the x-axis. And delta x, so W is minus F times delta x. How much is delta x? Delta x is where delta x equal. He didn't give me its 5 meters. He gave me x initial and x final. So from x initial and x final, I know that delta x is x final minus x initial, which is equal 18.2 minus 12.4. Delta x equal 5.8. Okay, so the work done by friction is equal to minus friction, which is 45 times 5.8, and the answer is minus 261. So this is how we apply the equation. Work is equal Fx delta x. What else did we learn last time? We also learned about different forms of energy. So energy, the different forms of energy we are responsible for in this chapter: kinetic energy, and we memorize it. It's half mv square. If an object is moving with a speed v, then the kinetic energy is half mv square. Okay. Gravitational potential energy. This happens when an object of mass m is at an altitude h from some reference point, like this rock, from the bottom of the valley. Okay, so this h will be its altitude, and I can calculate the gravitational potential energy, or what we call GPE, by applying mgh. Okay, and finally, elastic potential energy happens when we have a spring, a string, a rubber band. We mostly need to focus on a spring or a rubber band. When it is compressed a distance delta x, or when it is elongated a distance delta x, the EPE is half k delta x squared, where delta x is the elongated or compressed distance, and k is the spring constant that we know from Hooke's law. Okay. The only form of energy I will introduce now is mechanical energy, which is simply the sum of all types of energy. So mechanical energy is kinetic energy plus gravitational potential energy plus elastic potential energy. Sometimes it's only kinetic energy if the object is not at an altitude and it's not connected to a spring. Sometimes it's only gravitational potential energy if it's standing still, like in this case, it is not moving. So there is no kinetic energy. So mechanical energy is GPE. There is no spring here. So in this special example, for example, mechanical energy is only GPE, gravitational potential energy. For this lady here who is running, there is no rubber band, there is no spring, there is no altitude. She's running on a horizontal surface. So mechanical energy will be kinetic energy because she's moving with a speed v. Okay. So it's not, sometimes the mechanical energy is only one form of energy, or two forms of energy, or three forms of energy. So whatever forms of energy exist, we will add them up to give me mechanical energy. Now, this is a law which is called conservation of mechanical energy. If there is no friction, whenever the question tells you there is no friction, then mechanical energy is conserved. What does it mean? It means mechanical energy initial is equal mechanical energy final, which means mechanical energy at all points, it's the same. let's start solving exercises to see how simple this formula is. So while at a county fair, Katie tries the water slide. Okay, so this is a water slide, and this is Katie over here, whose shape is shown in the adjacent figure. I've put here the equations for all types of images. The starting point is 9 meters above the ground. So Katie was at 9 meter altitude from the ground. She pushes off with an initial speed of 2 meters per second. So once she started, she gave herself a push equal to meter per second. Assume the slide is frictionless. There is no friction. When I see a question like this and they tell me it's frictionless, implies mechanical energy initial is equal to mechanical energy final. Okay, I can apply this formula. Let's start by solving the exercise. Write the expression of mechanical energy of Katie at the top of the slide. Okay, so at the top of the slide, what does she have? She has an altitude of 9 meters. So she has h equal 9 meters. And she has a speed v equal 2 meters per second, right? So mechanical energy of Katie will be what? Because it has a speed, so it has kinetic energy. And because she has an altitude, so she has gravitational potential energy. So this is equal half mv initial square. Okay, sorry, half mv initial square plus m h. This is GPE. Okay, so let's see if we can replace stuff. Yes, we can. So this is half m. I don't have it, so I keep m. The initial is 2, so times 4 plus m. I don't have it, times 10, which is g, times 9, which is the altitude. Okay, so I get mechanical inner energy is equal to half times 4 is 2. So 2m plus 90 m. So mechanical energy initial, let's say this is mechanical energy initial or top. You can call it on top and on and down as you wish. So this you can call it ME initial or ME at the top. Okay, and I get this to be 92 mass of Kate. Okay, so this is the expression. It's an expression because it's not a number. This m, I don't know it. It's not a number. It's an expression. Part B, write the expression of the mechanical energy at the bottom of the slide. So at the bottom of the slide, we want to write the expression of the mechanical energy. So we say mechanical energy final in this case, or at the bottom, it's equal to, once there is no altitude, so there is no gravitational potential energy, but she's still moving with some speed. So it only has mechanical energy final. Okay, so mechanical energy final is equal to half m times v final square. This is the expression. Now, part C, determine this v final. Okay, we want to determine this v final. This is a problem where there is no friction. So no friction implies mechanical energy initial is equal to mechanical energy final, implies, instead of mechanical energy initial, I will put 92 m is equal to, by the way, here I forgot to put half. Okay, is equal to half m final square. Okay, m goes with m. M here goes with this m. Okay. So I get 92 times 2. I do cross multiplication here. 92 times 2 is equal to V final square. 184 is equal to V final square. Now V final is equal to square root or radical 184, and the answer is 13.56 meter per second. Okay, you see how simple it is? We just have to pay attention. These are two positions. In one position, we have kinetic energy. We have gravitational potential energy because it has the initial velocity and it has altitude. But when it reaches here, there is no more altitude. It reached the bottom. So it only has V final, okay? So mechanical energy final is only half mv final square. Mechanical energy initial is kinetic energy plus GPE initial. Then because there is no friction, these two are equal to each other. I solve, I get V final equal 13.56. Let's do another exercise. The solution is here. Let's do another exercise which involves a spring, okay? So a spring-loaded toy, it's a toy, is used to launch a 10 grams plastic ball. So they're giving me the ball M equal 10 grams, okay? Perhaps it's better to change it directly to kilograms because grams is not a proper unit. That we use here. The spring, which has a spring constant of 10 Newton per meter, so this is K, 10 Newton per meter, is compressed by a delta X by equal 10 centimeter. The 10 centimeter is 0.1 meter. I divide by 100. This is here, divide by 1,000. Here, divide by 100. Okay. When the trigger is pulled, so first it's compressed. Okay, so before the spring is compressed at distance delta X equal 0.1 meter. Okay, this is before. When the trigger is pulled, then it is released. The spring is released and shoots the ball back out. So it's released, and then when it reaches the X equal to 0, it pushes the ball. So after, what do I have? I have the ball moving with a speed V in V final. Okay, they call it V final. Before, they say V initial equal to 0. So there was no V initial. So what form of energy do I have before? This is a spring compressed and there is no V initial. So what form of energy do I have? Since there is compression of a spring, so I have EPE, okay? Since V initial is 0, so kinetic energy is 0. Since there is no change in height, so GPE is also 0. So the only energy I have initially is EPE, which is half K delta X squared. After X is 0, so there is no more delta X is 0, so there is no EPE. So after there is EPE is 0, but it's moving with a velocity half mv final squared. It's moving with a velocity v final, so there is kinetic energy. Again, there is no altitude. There is no altitude, so GPE is also 0. So this is my analysis. Now I want to solve what is the ball's speed as it leaves the barrel. We want to get this V final. Okay, so we have one formula because there is no friction. Assume friction is negligible. Once I see this, I say mechanical energy initial is equal to mechanical energy final. Initial, I only have EPE. This is equal KE. Okay, EPE is half K delta X square. Let's separate them just to see it clearly. And this is equal to half mv final square. Half and half, they cancel each other. Half and half, they cancel each other. Okay, what is v final square? So I get v final square is equal to, I do, this will be K times delta X square divided by M. This is equal K 10 times delta X 0.1 square right, divided by M, which is 0.01. I get the answer. V final square equal 10. V final equal 3 square root of 10, which is equal to 3.16 meter per second. Okay, let's do one more exercise. The solution is here. So let's do one final exercise. A skateboarder of mass M equal 55 kilograms. So I have the M, it's 55 kilograms. Wants to cover the upper edge of a half pipe. So he wants to go from here till here. He wants to go from here till here. Okay. The radius of half pipe is 3 meters. So what is this 3 meter? What is this 3 meter? This is H. This is H. This is 3 meters, as shown in the figure. The reference passes through the initial position. So here is the reference. Here is the reference. So H is 3 meters. So GPE is 0 over here at the reference. Part A. So we have H is equal to 3 meters. Okay. So part A gives the expression of the initial mechanical energy of the skateboarder as he was down here. Did he have any GPE? No, because it's on the reference. Does he have KE? Yes, because he's moving with velocity V initial. Does he have EPE? No, because there is no spring or string or rubber. So mechanical energy initial is KE, which is half mv initial square. Okay, this is equal half m55 times v initial square. 55 over 2 is equal to 27.5 v initial square. M times M. Oh, no M. Okay, this is mechanical energy initial. Part B, calculate the mechanical energy at the top. So at the top, what form of energy do we have at the top? So he will go to the top and stops or keep moving? No, he will reach the top and goes down. So he will stop, then goes down. If he stops, implies V at the top, V final over here is 0. So he doesn't have kinetic energy. Kinetic energy final is 0. and definitely there is no EPE. So the only form of energy at the top is GPE, which is mgh. So mechanical energy at the top is equal to, you can call it at the top or at final, whatever you like. This is equal to mgh. This is equal to 55 times 10 times h, which is a 3. And this is 1,650 joules. Okay. And part C, apply conservation of mechanical energy in order to get V initial, which you need at the bottom to cover all the way up. So we need to calculate V initial by applying conservation of mechanical energy. So we will say mechanical energy initial equal to mechanical energy final. Mechanical energy initial is 27.5 V initial square. This is equal 1,650. Okay, so V initial square is equal to 1,650 divided by 27.5. V initial square equal 60. V initial equal square root of 60. V initial equal 7.74 meter per second. Okay, so today we reviewed how we calculate a work done by a force, and we found out that if the angle between the force and the line of motion is 0, the work is the highest. Then as the force starts making an angle with the x-axis, it starts getting less and less until it reaches 0 if it's perpendicular to the line of motion. If the force is resistive, like a friction force, the work will be negative. Then we reviewed what is kinetic energy, what is gravitational potential energy, what is elastic potential energy, and we introduced mechanical energy, which is the sum of the three. Sometimes it's only one of them, depends on what forms of energy exists. And we solve exercises on all the concepts in order to understand, to practice these equations. Tomorrow, I will be solving more exercises in order to practice these equations more. So good luck and have a good day.